Hi everybody, welcome to lecture 1B for physics 151. These slides are about powers of 10 and scientific notation. I'm going to try to start each of my slide decks with a cover slide that will remind you of the topics in this particular set of slides, also the sections of our textbook that are related to that, and other materials that are on these topics as well. So before you go further in these slides, I recommend that you have handy a copy of tutorial number 1, the sample problems of 101. This one's actually short, it's just a page. Please either pull it up in another window or on your tablet, or print out a copy on paper. And for the end of these slides, I will use 3 of those short little problems as examples. As soon as you feel you've gotten the hang of things, the tutorial problems are just for practice, so you can stop at any time and move on to the online homework problems, which are worth credit. The first few questions of homework number 2 are also on scientific notation. So then I'd recommend that you do those as soon after you've watched this lecture. One quick note, in the future, I'm going to try and synchronize these numbers so that that way the lecture number and the tutorial number and the online homework number will match. Okay, at least the numerical part. Unfortunately, I got off a little bit here at the start, but I'll try and sync it up going forward. Okay, powers of 10 and scientific notation are a topic that many of you are probably already familiar with from your other science classes. So if you're already really comfortable, then that's great. You can zip through this and go straight to trying the homework problems. Otherwise, if you're a little rusty, then I recommend that you watch this as a refresher, and maybe you might pick up. I have some shortcuts to share with you, so maybe you'll pick up 1 or 2 useful bits from that. First of all, just as a reminder, when you see 10 raised to any integer exponent, right, then at least for positive integers and for 0, then that is the same thing as seeing a number which is written as a 1 followed by n zeros, right? And if we look over here at this little table, that's exactly what we see. We see that when you look at 10 to the 3, that's the same thing as a 1 followed by 3 zeros. 10 to the 12 is a 1 followed by 12 zeros. It even works for 0. 10 to the 0th is 1 followed by no zeros at all. Now, if you have negative exponents, right, remember that definitionally what that means, 10 to the negative 3 is the reciprocal of 10 to the 3. It's 1 over 10 to the 3. But it turns out when you turn that into a decimal and write it out, then that nice little mnemonic that just worked above doesn't quite work the same. It turns out that it's a 1 preceded by only 2 zeros before you get to the decimal point. Right? So 10 to the 6th is a 1 preceded by 5 zeros. 10 to the 9th is a 1 preceded by 8 zeros. So it's off by just 1. I'm not counting this 0 that comes before the decimal point because that doesn't have any placeholder meaning in the number. It's just there cosmetically to help our eye notice the fact that there's a decimal point coming right there. Okay? So it's just there as a visual aid, but it's not doing anything mathematically for the number. Please make sure that you memorize these words, the meaning of these English words as they relate to these powers of 10. So that way, whenever you see million, billion, or trillion, or hear those words spoken, you will be able to instantly convert to 10 to the 6, 10 to the 9, 10 to the 12. Okay, a 1 followed by 12 zeros, a 1 followed by 9 zeros, and so on. And I recommend that you memorize them down between 1 trillionth and 1 trillion. It turns out, and this is going to be necessary for the metric prefixes that we're going to talk about in the next lecture. However, there are metric prefixes. They go outside of this range. They go higher and lower. And those are used occasionally in the sciences, but not nearly as often as the ones that are in this range of a trillionth to a trillion. So these are the ones. These are the words that are the most important ones to memorize, because those are the ones that come up the most. All right. So what is scientific notation? As you know, in the sciences and specifically in areas like physics and astronomy, we often deal with extremely large and extremely small numerical values. right? So these numbers go on for many, many, many digits. So I have a couple examples right here. The diameter of the Earth, written in meters, or a typical mass of a bacterium, okay, written in kilograms. All right, well, what's wrong with this? Well, obviously, these numbers are very long, they're bulky, they're cumbersome to write and to manipulate on the page algebraically, and there's a good chance that we'll make mistakes as a result because we're trying to keep track of all of these digits. Also, scientifically, it's important for us to learn to, when we're trying to sort of interpret numbers and what they mean and sanity check the meaning of our results in calculations, it's important for us to be able to quickly grasp the order of magnitude of a number, right? In other words, is this number a few thousand, or is it a few million, or is it a few billion? How does it compare to the other numbers on the page? When you're blinded by this big string of zeros here, it's very difficult to do that. Okay? However, there's a solution to all of this, and that is scientific notation. Scientific notation is just a fancy way for saying take a number that is very big or very small and write it out as a multiple of a number between basically 1 and 10 times some power of 10. Okay? Now we take that power of 10 and we write it in a nice compact exponential notation. The number between that we're going to always aim to have this preceding number between 1 and 10, this part is actually has a name. It's called the mantissa. And then the exponential part with the power of 10 is the value of that exponent is just called the exponent. And notice that the units here are understood to apply to everything, the mantissa times the exponent, that whole thing together. It actually applies to both, right? But not separately, sort of as a whole. Sometimes you'll see parentheses written around the value, but that's not necessary when it's just a straight up scientific notation number and exponent. So the advantages of this are, of course, it fixes all the things we talked about earlier. These power of 10 numbers are short, compact, easy to write, less prone to errors, and they provide us with a really quick glance understanding of the order of magnitude of this number. When I first look at this number written out for the diameter of the Earth, it's hard for me, without counting up all the zeros, it's a little bit hard for me to grasp, oh, is this thing on the order of 1 million or 10 million or 100 million? But once we write it in this notation, 10 to the 7th, that's 10 million. Done, right? I can instantly grasp the order of magnitude. This example down here is far worse. I can't really tell at a glance whether this is in the range of billionths or trillionths or whatever. But once we convert it into scientific notation, I see, it's actually beyond that. It's beyond a trillionth. This is a quadrillionth of a kilogram. So we call this the order of magnitude of that number. This mass of the bacterium is on the order of 10 to the minus 15 kilograms, is what we would say. We would say the diameter of the Earth is on the order of 10 to the 7 meters, or 10 million meters. Now, on this slide and the next, I want to quickly cover some conventions, meaning traditions or customs, that we use surrounding scientific notation. First, when we follow that rule from the previous slide, we take a number that's long and cumbersome, and we just express it as a shorter number times a power of 10. It turns out that there's actually an infinite number of ways to do that, right? And what I've written here are a few of the possible ways to write the diameter of the Earth. Notice that mathematically, or to a computer or to a mathematician, numerically all of these are the same. They're all exactly the same. In other words, to a computer, 1.274 times 10 million is exactly mathematically equivalent to 12.74 times 1 million, or 127.4 times 100,000, right? However, we have a custom. We prefer to always write a number in scientific notation so that the decimal point follows the first non-zero digit. So notice that in all of these forms up here, there are a bunch of extra preceding zeros that are placeholders, right? And we want the decimal point to follow that first non-zero digit. Or down here, we want the decimal point to follow this first non-zero digit, which is the 1. Right? So that is the most compact notation right there. And the reason I say most compact is because you look at these, as you go high up on this list or low down, look how there's more and more digits being bulked up and added to the number. And the same thing happens down here on the list as well. Okay? So this is by far the most preferred method to write it as a final answer. Um, and the other advantage of that is, well, it turns out we're going to find out this has other advantages for significant figures, which is coming in the next lecture. But also, at a glance, it tells you the order of magnitude that this number belongs to. So we can see at a glance that the diameter of the Earth is order of magnitude 10 to the 7th, and not any of these. It's not 10 to the 10th or 10 to the 3. Suppose that you have a number that is in some sort of power of 10 notation, but it's not in the most compact form, the conventional form. Or suppose you're starting with a plain number, right? Suppose you start with 12,740,000. Then there is a shortcut that we can use to try and adjust that number into our desired most compact form. And the shortcut is this. If you move the mantissa's decimal point one place to the left, every time you do that, that's the equivalent of taking another factor of 10 out of the mantissa. We're going to take those powers of 10, those factors of 10, and pile them up into this exponential portion. And what that does is it increases the exponent by 1. So here, let's look and see what happens as we go up this list. As we take the decimal point and move it from this location one place to the left, then what do? We add. We take that 10, we pull it out of the mantissa, and we add it to the exponent, the exponential part, and we add 1 to the exponent. Move the decimal point one place to the left again, add 1 to the exponent. Move the decimal point one place to the left again, add 1 to the exponent. And again, and again. You see how it happens all the way up as you go up this list. The reverse is also true. If you move the decimal point one place to the right, then you subtract 1 from the exponent, and you go down the list as well. Okay? So if you don't remember this sort of shortcut in mnemonic, then what I recommend is that you sort of use a sort of sanity check instead, right? And for example, suppose that I don't have the shortcut in front of me, and I'm looking at a number like 127.4 times 10 to the 5th. And I want to move that decimal point 2 places to the left to get it in my most compact form. Off the top of my head, I don't remember whether I'm supposed to add or subtract 2 from this exponent. But let's just think for a second, what are we doing? When we're turning this mantissa from 127.4 into 1.274. So we're trying to make this mantissa much smaller. What should then happen to the exponent to compensate for that? I need to make the exponent much bigger. And the way I do that is by adding to the exponent, right? 10 to the 7th is much bigger than 10 to the 5th. Right? So once again, if my desire is to make the mantissa smaller to conform to my convention, then to compensate I have to make the the exponential value much bigger. Why is this? Because the actual physical value can't change, right? The diameter of the Earth doesn't change. So as we go up or down this list of equivalent ways to write it, the product of the mantissa and the exponential needs to be constant. So if I want to make the mantissa a bigger and bigger and bigger value, say going down the list, then I need to make sure I need to make the exponential smaller and smaller value to compensate at the same time. Finally, whenever you're expressing a final numerical value at the end of a problem in scientific notation, I really recommend that you do one last sanity check, right? One last reflection and ask yourself, does it make sense for the thing that this value is supposed to represent, right? So for example, this is supposed to be the diameter of the Earth. Suppose I made a mistake in my algebra here and I wind up with some value times 10 to the minus 7 meters, or 10 to the minus 3 meters, or even 10 to the 2 meters. Does it make sense that any of those distances, knowing how big a meter is, right, which is about a yardstick, does it make sense that any of those distances would be the diameter of the Earth? Instantly I can say no, right? That it's just unreasonable. It doesn't make sense. And if you're doing a problem where the answer to the problem is supposed to be something like the height of a person or the length of a bacterium, and you wind up with any of these values that are astronomically large, then you know also that something went wrong along the way. So this is a good habit of mind to develop for all physics problems, not just these scientific notation conversions. Check your final result against for common sense against the thing that it's supposed to represent. A couple more quick conventions. First of all, remember the whole point of scientific notation is to make values that are extremely large or extremely small easier to read and digest and write. However, what should we do with values that are not so big and not so small? Well, you should avoid scientific notation, right? Here are some values that lie in the range of here, it's a few tenths to a few hundreds. Notice how writing them in scientific notation makes them longer and more cumbersome and harder to digest and understand at first glance. Leaving the numbers in their original form is preferred. The rule of thumb I use is generally when the value is between a few thousandths, which I don't have an example here, but a few thousandths to a few thousand. So anywhere from like 0.005 up to about 5,000 or a few or even more, 8,000 or something. I usually prefer to write the number as a regular number and not in scientific notation because scientific notation makes it more bulky. Now there are occasionally exceptions why you might want to use scientific notation, even for like this case right down here. And that might be to make values match all of their units or match all of their powers of 10 exponents, or maybe to be really explicit about the number of significant figures. So, because sometimes it can be a little ambiguous whether trailing zeros are significant. So there are rare times when you might want to leave a final answer in a form like this. But otherwise, I recommend you cast final answers like that. And if I ever saw a final answer for a problem, if I was asking you to hand in problems where you show your work, and if we were grading regular homework like that this semester, then if I saw a final answer that was in this sort of a form, 8.2 times 10 to the minus 1, I would circle that and say simplify. Just write it as 0.82. The last thing is when dealing with computer inputs and outputs, the way computers deal with very large and very small numbers, floating point inputs and outputs, is to replace the times 10 to the by either a capital or a lowercase e. However, when you're using a pen or a pencil or a stylus and you're just writing by hand, then there's never any reason to write the e to write it as an e instead of as 10 to the 7. In fact, to write it as an e is bad form and potentially confusing because little e and big E have other algebraic meanings, perhaps, in our physics formulas, or mathematically, little e is also the base of the natural logarithm. So it just can add confusion. If you're not preparing a computer file for input or output, then you should always write times 10 to the. All right, so let's do some quick examples. First of all, if you pull up the tutorial sheet, in fact, feel free to hit pause right now if you want to pull up the tutorial sheet and have it handy. All of the questions on the tutorial sheet simply ask you to convert non-scientific notation values into scientific notation. So I just have 3 of them here as an example on this and the next slide. First, let's look at example A. 53,081. All right, well, you can approach this a couple of ways. One is to just at a glance try and recognize this number, this big number, as a small number between 1 and 10 multiplied by some power of 10. So just by inspection, we can look at it and say, oh, 53,081 looks like it's 5.3081 times 10,000, and I can recognize 10,000 as being a 1 followed by 4 zeros, so it's 10 to the 4. and we're done. The other way to do it is to start from is to use our shortcut that we were talking about for moving the decimal point to the right or the left. So start with the original value. Where's the decimal point now? Well, as we know, it's customary not to write it when you don't need to have it there when there is no decimal component or portion to the number. But it's understood as being just there to the right of the 1. And where do we want it to go? We want it to go over here to the right of the first non-zero digit, which is the 5. So that means we want to move the decimal point 4 places to the left. And our shortcut reminds us that that means we need to add 4 to the exponent. Well, what's the current exponent? Well, there's sort of an unwritten times 10 to the 0 out here, right? 10 to the 0 is just 1. So there's an understood times 1 out here to the right. So we have 10 to the 0, we add 4 to it, and we wind up with 10 to the 4. The steps are pretty much exactly the same for this very small number right here. We can either glance at it and recognize it as, oh, that's 24 times 0.00001, and 0.00001 is 10 to the negative 5. Or we can do the decimal point shuffle again, right? So we start off with, here the decimal point is actually visible, so we know where it is. And over here to the right, there's an understood times 10 to the 0. So I'm going down here to the bottom, I want to move my decimal point so it follows the first non-zero digit, just to the right of the 2. So that's 5 spots to the right. That means I need to subtract 5 from the exponent. And there. Notice that our shortcut rule works down into negative exponent territory as well. I didn't mention that earlier, but adding and subtracting values from the exponent works even after you get down to 10 to the negative values. One more example. The decimal place shuffle works really well when you have a value that's in some sort of power of 10 notation, but it's just not in our conventional most compact form. In that case, this will be a little more laborious to convert this back to a regular number and convert it back into scientific notation. Instead, we remember that the conventional rule is for the decimal point to be moved to the right of the first non-zero digit. So we see by inspection here that that's just to the right of the 9. So I want to move the decimal point 1 place to the right. And I remember from my my shortcut rule that means I need to subtract 1 from the exponent. So I do that, or add -1 if you wish. All right. Okay. If you forget the shortcut rule, you can try using a little bit of sanity checking and reflection and just ask yourself, oh, look, I made the mantissa bigger by moving the decimal point to the right. It went from 0.9 to 9. So therefore, I need to make sure I make the exponential portion smaller. So that way when I multiply these two, the actual physical value never changes. All right. So my recommendation now is, if you'd like more practice to see if you have the hang of this, do as many of the practice problems on tutorial 1 as you have time for, and check your answers against my solutions that are also uploaded. When you think you understand it pretty well, then go ahead to Online Homework 2 and do the first 3 problems on scientific notation, because those are the ones that are actually worth points. So if you think you got the hang of it, feel free to quit tutorial 1 whenever you want. All right, and that does it for this lecture 1B.